All right, hello. My name is Topi Leppänen. I'm a PhD student from Tampere University, Finland, where I work in a customized parallel computing group there, where among other things we maintain the POCL, the open source OpenCL implementation that was shown in the previous presentation as well. So this work is kind of about my side of POCL, where I've been focusing on FPGAs and ways of integrating FPGAs into this OpenCL implementation. And in this work, we were looking at the OpenCL pipe and if that could be a useful program model for creating these effective pipelines on FPGA. Yeah, so first a little bit of background on FPGA OpenCL implementations. And then I have some kind of issues with the current pipe specification that prevent us from using it or prevent us from creating these kind of nice pipelines on FPGAs. And some suggestions or extension proposal type of stuff there. And then at the end, I have a implementation case study where we made like a proof of concept implementation on FPGA. So there's these two major OpenCL implementation for FPGAs for both AMD and Intel. Currently, so in this work, I'm talking about the parallel implementation. So it's kind of, I'm not using the vendor implementations, but trying to make my own. And it's not like comparable to the vendor implementations in completeness in any way, but the idea there is to be a bit more cross-vendor in our support. But it's a work in progress type of implementation. So a little bit about the FPGA in general. So of course you have to separate host and the device in the OpenCL platform. So the FPGA card, so if you have PCI FPGA, it integrates to the host something like this, where the entire white region here is the reprogrammable FPGA, and you can use it to implement basically any circuit you want and describe it at the cycle level accuracy. You can create custom hardware in this way, and then you get to run it at 200 to up to maybe 700 megahertz. So that's kind of okay. So it's an order of magnitude slower than maybe CPUs, but you get to implement your own hardware, which is interesting. So typically OpenCL implementations for these PCI cards, they are split into a static and a reconfigurable region. So the static region contains some kind of boilerplate logic related to the external interfacing. And then the reconfigurable region, that's the actual OpenCL program. When you compile OpenCL program, the kernels in that get synthesized into hardware descriptions, and you generate the FPGA configuration bit stream out of those. The kind of main feature of these OpenCL implementations on FPGA is the really long compile time. So it's multiple hours. So it's not realistic to use the JIT compiling for FPGA implementations, and typically it's not used. So here's an example of 4 different kernels I have here. So all of these kernels are now part of some OpenCL program, and we have compiled that and generated the FPGA configuration bitstream. And once we have put that to the reconfigurable region on the FPGA, then on the host software we get this nice OpenCL kernel object that we can then program with the buffer kernel arguments. And I have explicitly drawn this DMA block here on the kernel side, just to emphasize that because it's a custom hardware, we can specialize also the memory access hardware there. So if this is doing like image processing, where it would be passing the image from one kernel to another, it will like write that to the output buffer using this specialized hardware, doing like large contiguous accesses. This is nice. So in this case, I don't have a cache here just because the size of the images is so large that it wouldn't be possible to implement on the FPGA. So this is just like putting it completely through the external memory. Then this is how you would then describe in the OpenCL. It is nothing special here. You have a producer kernel and a consumer kernel, and they're using a common OpenCL buffer object there, where somebody is writing there, and then the consumer is going to be reading there, and use the event to synchronize between them so that to avoid the race condition on the data. And the specification supports this very clearly, that the consumer kernel will be waiting there until the event is complete. So that works. It works. But then there's a different program model that could be useful for FPGAs, and I call it here a streaming style execution. It's like a finer grain synchronization level than the events. So you would be able to pass the data like partially. You don't have to have the entire image frame ready, but instead you can kind of have your computation going on there at the subframe granularity. And this, of course, minimizes latency, as was alluded to, for example, in the ARM presentation earlier, that in image processing pipelines, the total latency can be critical. And the question is then, could OpenCL pipe be used to support this type of execution model that I saw in the image there? So let's try to figure that out. So in the specification for the pipes, it's been there since 2.0, but it's now been optional in 3.0. It's kind of a FIFO-like structure. So you use the kind of read and write commands to push and pop packets. So these packets are like single integers or SIMD vectors of integers. So it kind of seems that it could be useful to implement this kind of fine-grained pipelines. So let's try to do this in like a small example here. So let's try to come up with the kernel programs for this. So we have a producer kernel program that has the pipe as a kernel argument, and then it just writes n data items to the pipe, and it has an additional busy loop there around the write pipe API because it's a non-blocking API. And the same thing in the consumer side, where the consumer will then just read it with the non-blocking API as well. Okay, so now we have created these programs, and we then would compile this for this FPGA. So we would generate the hardware for this and try to start writing the host software for this. And the question is, when we're submitting these to a command queue, let's say out of order command queue, the question is, should there be an event dependency between these kernels when we are submitting these? This is like a very practical question because I was faced with this kind of myself. But there's a kind of really no good answers here. So if this is the target you want to achieve at the top, this kind of execution, then if you include the event dependency, you will get something like on the left side, and if you don't include, you risk getting something like on the right side. So with the event dependency, this is just exactly equivalent to the earlier event synchronization slide I had. The event prevents the consumer from launching before the producer is in a complete state. So this is kind of very clear. So this kind of demotes pipes to be just a glorified version of a buffer. You have to use them exactly similarly as OpenCL buffers, which I think is a bit of a shame because they could be useful for more. So this increases total latency, and if you implement this on FPGA, we would like to implement this as a hardware accelerated pipe. The pipe has to be really large because it has to be able to fit the entire image data, for example. If you don't include the event dependency, you risk getting this kind of behavior from the implementation because the spec has kind of relaxed memory model on these pipes that the pipe contents only have to be enforced at the synchronization points, which are exactly the points defined by the events. So there's no guarantee that the data will get through the pipe to the other side. So you could get the deadlock, so probably shouldn't write your host programs this way either. And I think like Khronos conformance test suites confirm this, or this left view here, that they use the event dependencies there between the kernel launches. And I think Intel FPGA implementation also uses the events, and they recommend using the event between the producer and consumer kernel, but they I think they just ignore this part of the specification and they start the consumer anyway earlier, which may be okay because they are able to give user the fine-grained task pipeline that the user probably wants to have. So Intel has made a SYCL extension proposal for pipes. I think it's in draft state. They have extended their earlier OpenCL tool for SYCL, and they have this proposal that the read and write operation must eventually be visible from producer to consumer. It tightens the memory model for the pipes a little bit, or quite a lot, and so it forces that implementations must eventually push the data through the pipe. So implementations cannot just never push it through. But this is a bit uncomfortable or inconvenient for the implementations because we can no longer assume that all the data that the kernel needs is ready when it launches. Because earlier, with the global memory object like buffers and pipes, the kernel can assume that all of the data it's ever going to need is already in the global memory before it starts. This is no longer the case because some of the data could still be dripping in little by little while it's running. And you could have a multiple of these, like a really large graph of these kernels just running one after another that would push to like pipe of size 1, and you would have to context switch between the kernels like quite often. And there's no limit of if you have, for example, single kernel, you can just pipe it together to itself multiple times and create arbitrarily large graphs. So there's probably should be some way to limit this. So the way we thought of is to have for the building kernel specifically, first that one. So you would, for every building kernel, you would say how many hardware contexts does it support? And that would basically limit the size of the graph that you are able to describe with it. And the similar parameter for the compiled kernels, like max concurrent pipe kernel instances, it would basically just limit the size of the graph. How many nodes can the graph have without event synchronizations in between? Because then those will pass through. And if you set this to 1, but if the implementer sets it to 1, then it's equivalent to the old behavior where the user shouldn't expect that the data will get through because the implementation says that it can only support one hardware context for this. Oh, that was about the spec suggestions or extension proposal type of presentation. So now I have a small proof of concept implementation for the OpenCL pipe that we made with and integrate into POCL. So first, this is how the FPGA vendors have implemented the OpenCL pipe earlier. So AMD doesn't have this anymore, but they used to have this, and I think Intel had this until the very last deprecation notice. Well, they still have it in their tool. So during the compile time, the kernels are connected together with like this very efficient streaming interfaces. And these are like hardware interfaces. So in practice, it's just going to be like data signals going from left to right here, and then there's going to be 1 bit for ready and 1 bit for valid to arrange the data movement there. So it's very fine-grained and very efficient to implement. And you can get really nice throughput and latency with this one. The tricky thing with this one is it's not compliant to the spec at all because you have to know this connectivity at the compile time. So if you have multiple kernels, you shouldn't have to define this at the compile time. So I think there's two options here. Like if you want to support this kind of feature, you have to standardize this somehow or make an extension of it. Maybe similar to what already was in OpenCL 2.2 C++ kernel language. Or you could implement this somehow differently in a more dynamic way that would allow you to allow you to have this dynamic connectivity in your implementation. And so the way we thought of implementing this is to have like a directable crossbar there that is synthesized on the hardware side there. So when you have the kernels on the chip, then all of these interfaces can still be the efficient streaming interfaces. It is very simple to implement, and you just reroute the signals there dynamically based on how the user has connected them together using the set kernel arc API. So by this we were kind of able to solve this dynamic connectivity problem. So we used this axis stream side channel called tdest, which is basically just the ID saying to which direction should this go. So in this case, it would be with 4 pipes, it would be of size 2. It would be 2 bits of side channel information that gets passed through with the data. So, and you can then dynamically route this together. So the main storage for the pipes is now going to be in this FIFOs there on the white blocks there. And so of course the size is still kind of, there's a maximum size that has been set when we synthesize the hardware, but we just have to make sure that we fail any CL create pipe calls that when the user tries to ask for more than is available. And that should be okay according to the spec. So we implement this same pipeline or same application that we had earlier of this kind of image processing kernels. Now we implement it with this dynamic redirectable pipe component in middle. So all the blue arrows here on the right side of the kernels, these are the write-only pipes. They're connected to the left side of our dynamic component, and then all the blue arrows or the red arrows are the read-only pipes on the right side. And from the OpenCL host software, we now get like honest for the software point of view. It's just these OpenCL kernels there that it can use pipe arguments for an use set kernel arc to construct a dynamic computation graph. And you could come up with some applications for this, but at least this is now more spec compliant than the vendor implementations earlier, because you are able to change the connectivity at runtime. And if you look at the earlier suggestions about the building kernel resources, in this case, I have 2 broadcast kernels. That is because the original application would need 2 of them. So that's why when I was creating the hardware, I implemented two hardware broadcast kernels there on the chip, and they're kind of in parallel there, and I can use them both in parallel. So each of these kernels are kind of simple hardware accelerators that there's no ability to context switch between them. So I would have 2 separate accelerators there just to have the 2 contexts, hardware contexts. And then we can evaluate. So we can compare our earlier buffer-based implementation to this kind of static implementation, which is the equivalent to our kind of similar to the vendor implementation so far, where you statically connect the kernels together. And then our own implementation here that I just described. And you would expect that maybe the static one is going to be the most optimal one. It has less overhead, and that is the case. So if we take, in this case, I have 4K image streaming through it, and I'm measuring just the latency for now from start of execution to end of execution. So this static connectivity streaming is about 4 times faster than the buffer-based implementation, just because it avoids the external bandwidth penalty that has to be paid in the buffer-based solution. And then our implementation it's not as close to the static implementation as I would maybe like, but it's still noticeably faster than the buffer-based implementation. So that's nice. The reason for why this is not that close is, I think, currently the reason is that this axis stream crossbars, I have not optimized them yet. So I think this is bottlenecking the performance a little bit. I think I should be able to make this more optimal in the future. In terms of area overhead, it adds about, compared to the static configuration, it adds about 4.4% out of the total device resources, which I think is kind of acceptable, at least on this very large FPGA. So this is the Alveo U280 FPGA, which is a large FPGA. So I think this is kind of acceptable price to pay in area for this dynamic connectivity, because in the host software you truly get this retargetable pipes. This is some slides about potential future work we are looking at. So how to support compiled kernels as well, because earlier we were kind of ignoring that side of it. So how does the actual kernel side compilation would work here? So we were using built-in kernels just to simplify it a bit. But for example, if you would have this multiple reconfigured slots for the kernels or OpenCL programs, whichever you want to implement it, you could also use this kind of dynamic component there in the mix in order to stream data with the pipes from one region to another. Another idea here is that it's no longer FPGA, but you would just harden this crossbar and make like a system on chip where you have multiple ASICs or something like this. And you would integrate the streaming interfaces to the processor data path. So I was thinking of making integrating it at the function unit level or register file level. There's multiple options there. And in this case, this could support a maximum of 4 concurrent instances without any additional context switching. So to conclude, I think we kind of showed that the pipe specification is not well suited for these fine-grained streaming type pipelines due to the relaxed memory model. But fixing it could be kind of interesting thing to do, because it would enable these really efficient hardware interfaces to implement the pipe. And just to test this, we create this dynamic pipe component to evaluate this dynamic pipe connectivity. Yeah, that concludes my presentation. Thank you.
Hi, 2 questions. First, for the kind of static versus dynamic pipe situations, did you notice what was the effect of Fmax on the synthesized designs between static and dynamic cases?
Yeah, that's a good question. I have it in the paper, but I left it out from this. There was some penalty there, but I left it out because neither of those were like fully optimized to the maximum they could ever achieve. So it's kind of a work in progress number. But there was some penalty, like maybe 30 megahertz just in this.
That's not too bad.
Yeah.
And then second question. So it seems like some of these issues aren't really with pipes per se, but more gaps in the OpenCL specification around specifying kernel concurrency, in that
yes,
really here what you want to be able to specify is that these kernels must be concurrent.
Exactly. Yes, that's right. And this it should be made clear in the, if this would be formulated as an extension, for example. So it should be made clear exactly this, that it's now kind of implied by my suggestions here, but of course it should be made more clear.
First, maybe a little comment. So actually I was the author of the pipe specification, and so you can both thank me for having it or hate me as well for not satisfying your requirements. So that's can both get claims and blames. So you can welcome to talk on offline to tell you more. So one thing that definitely didn't really make it into OpenCL specification is the graph portion, right? So how do you know which kernels are going to run? But the idea how other people and some FPGA vendors at the moment worked, they use a kernel and kernel. So if you do kernel and kernel in the same program, that actually gives you the graph.
So the kernel to what is it?
So feature kernel, so kernel and kernel feature in OpenCL 2.0, which is now optional OpenCL 3.0. So it allows you to specify one kernel do inside the kernel code and queue of another kernel.
Yeah.
If you do all of this in the same program, that actually tells you the whole graph. How implementation implements it, that's a separate thing, right? So for example, FPGA implementations, so could say, oh, this is actually my graph. Now I know what is concurrent and whether I can run this. And then of course, there's some other little missing things. You want program scope pipes.
Yes.
And you also, want some kind of extra memory model that allows you, as you mentioned. So you haven't pursued that yet. But I mean, that I would suggest that what do you think about pursuing that as a one way to do graph? Of course, there's more graphs now. There's the SYCL graphs and CUDA graphs and all that stuff, right? So rather than maybe inventing something new, can we go towards some more standard graph specification? That's actually what we also had and didn't really make it that way. So that's Khronos answer of graph in 2.0 was kernel and kernel.
Okay, yeah. That's interesting, and it's not kind of the direction I was going to go, because that's like the it still relies on the offline. It's like the offline compilation point of view, where you offline compile. You have to know the kernel, and then you offline compile the entire graph, right? And that's how the FPGA vendors implement it currently.
Well, you see all of that as a single program. So you can do offline compilation on the. So how you implement kernel and kernel FPGA? That's a FPGA vendor question.
Yes,
but the expression form, right? Just one program that gives you entire graph.
Yeah, that could work already. Yeah, I agree.
So just comment on that. So FPGAs are really kind of weird in that the mental model doesn't entirely fit, because even the notion of kernel instances is kind of misleading, especially in cases where you use pipes. It's really, you have one instance of the kernel that lives for the lifetime of the entire application. It's these always running kernels, and that's another thing that doesn't exactly quite fit nicely into the OpenCL model. So all the FPGA vendors generally add some extension or annotation on a kernel saying, auto run, or, there's a while true loop in it or something like that.
Well, on that front, we have fine-grained shared virtual memory, right? So you could dispatch a kernel and then just push data from CPU, and that kernel will consume the data, even though it's already running. You have full semantics of memory model, which is another plug since I was OpenCL memory model chairman. So we have that since OpenCL 2.0. Yeah. So I think there are some small things that we can fix without redoing everything. That's and then things will actually finally work.
Yeah, but my idea here is that to comment what he said, is that my idea is to see like how far can we, if we do things in a more OpenCL way, of like not having to do this kind of makes the same assumptions as the vendor implementers have made. So I want to maybe focus on that side as well, and let the vendors focus on the specifying their behavior. They can do that themselves. I've been kind of on the trying to work on other stuff than them.
Can you go back to your evaluation slide?
Yes.
So for this application that you demonstrated here, do you have all these kernels, and they all, like for the bottom implementation, you have all these kernels and they're all able to communicate with each other through your interconnect. But is it possible that, like, are some of these kernels never going to communicate with each other, or like you've configured it such that they could?
In the last case.
Sorry?
In the last case, you mean?
Yes, in the last case.
Yeah, so in this case, there's no extra kernels. So because just to make it equivalent to this one, so there's just the same amount of kernels. But yeah, it depends on the host application. So this kind of gives the host application more freedom because it can change it. It could construct a graph at runtime and it could compute anything with it, or it could connect them in other directions. It might not make sense in all applications, but could be useful for something.
Right.
Yeah.
So, but I guess something that I'm sort of getting at is what if you had multiple of these kind of super interconnects? So you specify these kernels can communicate, but these probably won't. So you kind of avoid having this central bottleneck for all these all these streams, and then maybe you also kind of are able to you're able to route things.
Yeah,
more
exactly.
easily.
So that's actually really good point. I had this idea of, because you could build this middle component like hierarchically, and you would have this when you have this chiplet FPGAs, you would have like one of these on every chiplet, and then you would connect them through the chiplet in like lines, like through the separate connections as well. You could do kind of hierarchical stuff there as well, just to make some pipes faster than the others, and just things you could build there to scale this up to like 100 kernels. But I don't know how many kernels you would realistically want to have.
Okay. And then also like the other thing I kind of wanted to ask about, so it's the fact that you can have this sort of static schedule, kind of like you have a configuration too that uses the static pipeline.
Yes.
You wouldn't actually use what you're proposing here in that circumstance, because that's, as we saw in the results, that gives you the best performance and probably uses less resources.
Yes, of course, yeah.
But like,
Yeah.
you know, for another application, like you were saying, you might have all these kernels and want to have more dynamically route data
Yes.
in a different sort of application. Or like, it would also, maybe the secondary benefit would be you don't have to reconfigure the bit stream to run this ultra optimized version either. Oh, okay, yeah. Okay. So yeah, I just wanted to.
Yeah, that's exactly, you were exactly right in your analysis. That's right. So if you know this one, if you have like a command buffer or something, and you know it ahead of time, you are compiling. Of course, you want to compile it this way. There's no point to add the dynamism if you don't need it. So it's a special solution, I think.
Okay.
Yeah, thank you very much.
Thank you.